Hey, welcome to your favorite calculus class. We're going to look at rates of change and tangents to curves as we introduce calculus. So what is calculus? It's the mathematics of change. Okay, so they say that mathematics prior to calculus is a very static mathematics, whereas calculus becomes a very dynamic mathematics. Okay, so you can look at, with dynamic mathematics, you can look at velocities, accelerations, tangent lines, slopes, all these things in order to model some real life situations. Whereas with pre-calculus, you're really, like I say, kind of a static mathematics. So for example, you can, with pre-calc mathematics, you can look at like average velocities, right? Or if you have a constant velocity, you can analyze it with pre-calculus. But to look at the velocity of an accelerating object, you need a calculus. You know, you could say, hey, I'm going to jump out of an airplane at 2 seconds. What is my exact miles per hour at that point? Right? That you do that with calculus. Very dynamic. Slope of a line, you can do with pre-calc, but the slope of a curve, you're going to need calculus. So, and I could go on and on with these, but curvature of a circle is constant. You can do that with pre-calc, right? We can analyze circles and stuff. But the variable curvature of a general curve, you need calculus. You know, so for example, the slope of that tangent line or the area under the curve, that kind of stuff. So with calculus, what we're going to do is we're going to start out talking about some limits, especially in the next couple sections here. And there's a limiting process. We use our pre-calculus mathematics that we have. We use a limiting process to get us to the dynamic calculus. Okay. Let me give you an example. Let's start out with looking at some average speeds for a minute. So Galileo discovered that an object at free fall, again ignoring air resistance, and gravity only as a force, falls this, where t is your time, y is the distance fallen. Okay. So a moving object's average speed, let's find that. So here I've got a quadratic here. Here's our y equals 16t squared. So for example, at 1 second, you know, if I plug 1 in for t, I got 1 squared times 16, 16, right? It's fallen 16 feet. If I plug 2 in for t squared 4 times 60, 64, it's fallen 64 feet. So what's the average speed for the first 2 seconds of a fall? So for the first 2 seconds, well, at 0 seconds, and if I go up to 2 seconds, oh gosh. So from 0, which I've fallen 0 feet, to 2 seconds, I've fallen 64 feet. All right, this is feet right here. This is seconds, feet. What's my average speed, right? In other words, what's my feet seconds, right? What's my change in y, this is in feet, over my change in the time, which is in seconds, right? This is what we're wanting to know. So our average speed here would just be y2 minus y1, the change in the distance fallen, over the time 2 minus the time 1, right? This is t1, this is y1. This is the second times 2 seconds. It's fallen y2 64 seconds, right? So I'm going to get that change in y over change in t. So my average speed during the first 2 seconds, so y2, there's my 64, so I'm just finding a slope here. That's all we're doing. We're finding the slope of the secant line. The change in the distance fallen, right? The change in y over the change in time, right? It's average, so it's our slope here. 64 minus 0 over 2 minus 0. So 64 over 2, 32, this is feet per second. So during the first 2 seconds, from 0 to 2 seconds, it averaged 32 feet per second, right? So we could do the same thing if we went from like the first second to the second second. Like let's say we went now from 1 to the second second, right? So what's this? So from 1, which means I've fallen 16 feet, to 2, 64. What's that slope, right? What's the slope of that line? What's the change in y over the change in t? 64 minus 16 over 2 minus 1. So it looks like here we end up with, what's that, 48 feet per second. So it's a little steeper, right? So 48 feet per second is my average speed. Again, I don't know my instantaneous. So what if I was actually asking right at 1 second, like right here? What's the slope of that line? Right at 1 second. How many feet per second? What's my velocity right there? What's my speed right there at 1 second? Well, that's a calculus question, right? So, but what we could do is we could estimate it. We could take this, we could go from 1 to 2, and we could bring that down until, right, this is at 1 second, until we get a more closer approximation. Like this is a decent approximation, 48 feet per second. This is a little better, but as we move that point closer, right, obviously as we get right on the point, that'll tell us exactly how many feet per second we're going. And that's what this table's showing you right here. That was just the answers that we went over. So if we looked at it from, this is the 1, 16, right? And our interval was 1 second, so we went to the 2, right? We knew that was 48 feet per second. But what if we only went out to 0.1 and we found that slope is 33.6? What if we went even closer, right? And again, so if I can't draw this very, I'm sorry, I'm struggling drawing today. As I bring it closer, right, I get closer. As I get the point even closer, now I only go 0.001 away. I get closer and closer and closer. What do you think it is right there, actually at 1 second? Looks like it's getting closer and closer and closer to what number? Looks like 32 feet per second to me. All right, that's what the data is telling us. Ignore that. So the average rate of change is y2 minus y1 over x2 minus x1. Right, our slope. Average rate of change is a slope. Now, if you're talking with a distance and interval of h out, okay, that's what this is. This is notating. If I have here to here, this is my x, f of x. Oops. Here's my, and if I go out, so here's x and y, x, f of x. If I go out a distance h, right, this is a distance h. So now I'm at x plus h, whatever that is out here. I'm just going to call x plus h distance. Right? Initially, we went from the 1 second, and we went a distance of 1 second more. H was 1 second. We went to 2 seconds. Right? This is just notating whatever h we pick. So this is the point x plus h, comma, f of x plus h. Right, so this is just saying y2 f of x plus h minus f of x, right, y2 minus y1 over x plus h minus x, right, x plus h minus the x. Notice that the x's cancel, right? So here's just another picture, x1, x2. Here's our secant line. Alright, start changing y over changing t. That's just another picture of that. Alright, so let's look at this here as point Q approaches point P. So as we use these secant lines to approximate the actual tangent line, we got to bring this Q point, in other words, the distance between here and here, our h distance we call it, we've got to bring that in, right? So we're let's say this slope is, I don't know, 5, whatever it is. And I'm trying to figure out that tangent line. So I say, well, with pre-calc, I can only find the slope of the secant line. I can't find the slope of the tangent yet. So let me bring that down. Now that slope, that looks a little closer. This slope is 4, but notice I'm bringing this in. Now it's only this h distance, right? I'm bringing it in. That's a little better. I bring the point Q down, down. I bring the Q closer. As I get closer and closer and closer, in other words, as h distance goes to 0, I will get the slope of the tangent line. Okay, and we call that a limiting process. We're taking the limit as h goes to 0 of y2 minus y1 over x2 minus x1. And that's your slope of the tangent. Okay? And here's just a picture of a circle. If you remember, we had tangents and they were perpendicular to our radius, right? But it's not so simple when we got just some curve on a graph to find the slope of the tangent, right? It's not so simple. We have to use this limiting process. So we got to bring that Q point closer, closer, so that secant line slope, the slope of the secant, becomes a better and better approximation of the actual slope of the tangent. Okay, we got to bring that in. Okay, so let me do one more quick overview with this definition before I go to the example. Erase this. So with a curve, sorry, draw my own here. If I'm trying to find the slope of the tangent, right there, slope of the tangent. Okay, I'm trying to find that. I'm going to use slope of the secant. So I'm going to say, okay, I know this slope of the secant. I can find that. I'm trying to figure out this slope of the tangent. Well, let's start with this limiting process. So I say, okay, there's my point x. This is x, f of x. I'm going out a distance h. So this is distance h. So in other words, this is the point x plus h. So this is the point up here, x plus h, f of x plus h. So I say the slope of the secant line is y2, f of x plus h, minus y1, f of x, all over, so y2 minus y1, over x2 minus x1, x plus h, minus x. Notice the x's are gone. That's the slope of the secant. And then I bring it closer, right? I'm going to bring it closer, and I'm going to do it to there. That's a little better approximation. Then I'm going to do it to there, a little better. But it's getting pretty close to the slope of the red. So what we do is we run the limit process. We say, let me let this h distance, right? This distance is coming in. This h distance is going to 0 of f of x plus h minus f of x all over x plus h minus x. In other words, all over h. And that is my slope of the tangent line. Okay? So it's the limit as h goes to 0. We call that limit as h goes to 0. So here's an example we're going to run together. Let's see if we can make some sense of this. So I have this y equals x squared minus 5. And at the point 2, negative 1, let's see if I can draw this. So here's right here. Okay, so at 2, negative 1, I want to know right here what's the slope of that tangent line. What's the slope of the tangent line? So the slope at 2, -1. So I'm going to go slope of the tangent is the limit as h goes to 0 of f of x plus h minus f of x all over x plus h minus x. Again, that x is canceled. So what I need to do first is find f of x plus h. Now we know f of x, or y, is x squared, x squared minus 5. So f of x plus h would be x plus h squared minus 5. In other words, x squared, rather than just doing the old FOIL thing, plus xh plus hx, so I got two of those xh's plus an h squared, and then minus 5. So that goes right here, x squared plus 2xh plus h squared minus 5 minus, now I'm going to subtract the original function f of x, put that in parentheses because I got more than one term, x squared minus 5 is our original function, all over x plus h minus x. Well, again, the x's are gone, I just have an h down there. Okay. Now when I distribute this, notice my x squareds are going to be gone. My minus 5, and that's a -5, plus 5, that's gone. So what I'm left with is 2xh plus h squared all over h. Now I'm letting this h go to 0, calling it a limiting process. Again, we'll work more with the limits later. But what happens is I can't just allow h to be 0, because if I plug 0 in, notice I have a 0 on the bottom. I have an h on the bottom. So what you want to do is you want to work with this algebraically. Oh my gosh, come on. And take an h out of the top, out of each of those if you can, and you can. So that cancels. Now when I allow h to be 0, now I can plug it in, it's no problem. I have 2x when h is 0, right? So now I'm substituting h being 0, and I get 2x. So the slope of the tangent is 2x, but where's it at? It's at the point, now I use the point, 2, -1. So that's the equation of the tangent line, anywhere I want. Where do I want it at? This x value. So the slope is 2 times 2. The slope is 4. So I'm like, oh, that means right here, that slope is 4. That slope is 4. I found the slope of the tangent line's equation. I plugged the 2 in for x, and I got a slope of 4. Okay, I got a slope of 4. So now I can finish this thing off. If I can get a little room here. Slope of 4. Sorry, I don't. So I have a slope of 4, and it's at the point 2, -1. So here's the step 2. So step 1 was find slope of the tangent. All right, and we used the limit as h goes to 0, f of x plus h. Oops, oh my gosh. X plus h minus f of x all over x plus h minus x, right? That's what we did. And we found that the slope was 4. So number 2, now what's the equation of that red line? What's the equation? Well, we have a point, 2, -1. We have a slope of the tangent. We know the slope, the steepness of that line is 4. We can use point slope form from pre-calc. So y minus the y1 equals our slope of 4, x minus 2. So y plus 1 equals 4x minus 8. Subtract 1 from both sides. Y equals 4x minus 9. Okay, there is the equation of that. line, right at 2, -1 of the tangent line in red. Okay, let's do another one. Find the slope of the curve at -x³ plus 2. So you got this -x³ plus 2. It's kind of like that type of deal at 1, 1. Ugh, struggling here drawing today. Come on. At 1, 1. So first thing is we got to find the slope in blue, slope of the tangent line. So number 1, slope of the tangent line. The tangent line is limit h goes to 0, f of x plus h minus f of x all over x plus h minus x. Again, the x's are gone. Now our f of x is -x³ plus 2. So what would f of x plus h be? Well, plug in x plus h. So we got to go through that. Pretty tedious here. And so you'll end up with, let's see, you're going to distribute these, put those, you got x squared plus 2xh plus h squared, and then you're going to multiply that by x plus h. Don't forget you got a plus 2 on the end. I'm going to forget about the negative for a minute in front, but I'm going to multiply that through, and then I'm going to take the h through. So we got x cubed plus 2x squared h plus xh squared plus, now I'm going to take the h through, x squared h, 2xh squared plus, I'm going to have to come down here, h cubed, parentheses plus 2, sorry about that. And then I'm going to distribute the negative through to all those and combine them. So I got negative x cubed. And notice I got a 2x squared h and another x squared h. I got 3 of those. And I got negative out front, so minus 3x squared h. And I've got an xh squared. I got 2 more xh squared, so I got 3 of those, but I got negative in front. So minus 3xh squared. And I got this h squared, h cubed, so minus h cubed. And don't forget I got the plus 2. Okay, there's f of x plus h. Minus, now I'm going to minus the original, negative x cubed plus 2. And this is all over h. And don't forget that we're taking the limit on this as h goes to 0. Right? Now, notice when I distribute that, I got a plus x cubed, and I got a minus 2. So that's gone. I got a 2 and then a minus 2, so that's gone. So I'm left with negative 3x squared h minus 3xh squared minus h cubed all over h. I'm taking the limit as h goes to 0. Now I can't let h be 0 right now because I got a 0 on the bottom. I got an h on the bottom. So again, I take as an h out of each of the top, or I factor out as much h as I can. Looks like I can take an h out of the top, and I have negative 3x squared minus 3x h minus h squared is all over h. So now my h's cancel, and now I can finally let h be 0. I got negative 3x squared minus 3xh minus h squared. So when h is 0 right here, those terms are going to be gone, and I'm just left with my slope being negative 3x squared. Now my slope is negative 3x squared, but where's it at? At what point? At 1, 1. So at 1, 1, here's my x I got to plug in. So negative 3 times 1 squared, I got negative 3. My slope is negative 3 of this, I'm going to make it red now, red line. My slope is negative 3. Okay, that's the slope of the tangent there. So now that I know that, I'm going to have to clear up some space here. I know my slope's -3, and I'm trying to get the equation of the tangent line. Slope -3 at the point 1, 1. Let's write the equation of the tangent line. Add 1 to both sides. Y equals -3x plus 4. That is the equation of that red line, which that tangent line has a slope of -3. All right, let's do an application here. So here's just a graph. We have a growth of a fruit fly population in a controlled experiment. The average rate of change over 22 days is the slope of the secant. So it's showing you over 22 days. So from the 23rd day, it looks like there was 150 flies right here. Okay, and then at the 45th day, there's 340. So it looks like it's averaging 8.6 flies per day, right? It's averaging 8.6 flies per day. So what is the actual rate on the 23rd day? So I say, well, I know this was 8.6. That's the 340 minus 150 over 45 minus 23, right? This is 8.6 flies per day. That's what that ends up being, right? And that was for that 22-day period. So let's do a little better approximation to try and get to the red. Let's just go, what's the slope of that one? Well, it's 10.6 flies per day. Let's go from 23 to 35. That's a little closer to the red line slope, right? So as I get closer and closer and closer, now that's only 5 days away. I'm sorry, 7 days away from the 23rd day to the 30th day. It looks like 16.4. So that's a pretty good approximation of the red line. So I'm like, 16.4 using my pre-calculus, which is all the information I have. It looks like the 23rd day, it's going up, 8.6, 10.6, 13.3, 16.4. So it's probably a little higher than this, like maybe 16.7 flies per day is the actual slope of the red line, right? It's actually the instantaneous rate of change. We call that. It's the instantaneous rate of change. But we approximated it, right, as best we could using our secant lines. Well, thanks so much for listening. I hope that gives you a little bit of an introduction. We'll expand upon all of these topics today that we talked about in this section. Thanks. We'll talk to you later. Bye-bye.